All right, so what we're going to do in this video is actually use the knowledge that we got from notes 3 and try to find out if we can find the voltage, current, and resistance of different components in both series and parallel circuits. So let's take a look at some example problems and see if we can do that. The first example that we have is this particular circuit. You can obviously see that this is going to be a series circuit, not a parallel circuit, because if we start from the battery, which we have right here, and follow the line all the way around here, we can see that this path does not diverge in any location. It is just one path, so this is indeed a series. So what we're going to do is try to remember the rules that we have for series and parallel circuits to see if we can find out what the voltage is in resistor 1 and resistor 2 and what the current is going through resistor 1 and resistor 2. So the first thing that we have to do is recall the rules for series circuits. And so those rules, if you remember, voltage for the entire circuit is going to be additive. So what you're going to do is add the voltage from resistor 1 and add the voltage that's going through resistor 2, and that is going to equal the entire voltage of the battery, so 9 volts. All right, so what we're going to do first is to see if we can start filling out this chart. We don't know how resistor 1 and resistor 2 are splitting up those voltages just yet. They are not equal. Okay, so let's say these resistors were, instead of a resistor, there were light bulbs. Okay, so they're not going to be equal light bulbs. They're going to be different values because their resistances are different. You can see that resistor 1 has a resistance of 1 ohm, and resistor 2 has a resistance of 2 ohms. Okay. We can't just add them up yet because we want to make sure that we know the rule for sure when it comes to resistance. So we'll get to that in a little bit. But one thing that we also can fill out in this chart that we have is the total voltage. Okay, so we have this battery here, and we know that the total voltage is going to equal 9 volts because that's what's labeled on the battery. All right, and once again, we don't know how exactly that's going to be split up between resistor 1 and resistor 2. But let's see if we can figure out any other rules for the series circuit. So we went through the voltage one. The one for current basically tells us that the current at any location is going to equal, is going to be the same value basically. So the total current is going to equal to the current at resistor 1, which is going to be the same current at resistor 2. So the current is going to be the same. No matter what location we're in, current's going to be the same. And the final rule that we have for series is resistance. Okay, so we know that the total resistance of the current, of the circuit, is going to be additive. So we're going to have to add the resistor 1 plus resistor 2, and that's going to give us the total resistance. So now what we can do is come back to this and see if we can add this up. So 1 ohm plus 2 ohms gives us, of course, 3 ohms. So that's the total resistance. All right, so now where do we go from here? We don't have any other values and we can't really calculate anything, but we do know we can apply Ohm's law to this. So Ohm's law, if you remember, is equal to V equals I times R. Okay, V equals I times R. And this also applies for the total. So V total is equal to I total times R total. Okay. That being said, we have V total, it's 9 volts, and we have R total, it's 3 ohms. So we know that 9 volts is equal to I total times 3 ohms. Okay, so if we wanted to find I total, that's pretty easy. All we have to do is rearrange this equation so that we can find that I total is equal to 9 volts divided by 3 ohms. So in this case, 9 divided by 3 gives us 3 amps. All right, so we found the total current. And from there, we can also fill out the other currents as well, because if we come back here to the series rules, we know that the total current in the circuit is going to be the same everywhere. Okay, so if the total current is 3 amps, we know that the current going through resistor 1 is also 3 amps. And we know that the current through resistor 2 is also 3 amps. All right, so we're making progress here in our chart. We found the resistance and the current going through each resistor. Now it's a matter of using Ohm's law. So this equation, again, probably the most important equation in this unit. We're going to use Ohm's law again to figure out what these voltages are. Okay, so 1 ohm times 3 amps will give us the voltage, and that's going to be equal to 3 volts. 2 ohms times 3 amps gives us 6 volts. And then one final thing that we can do to double check that this actually checks out, we know that the voltage of the entire circuit is equal to all the components added up. So just making sure that 3 plus 6 equals 9, and that's how we know that we've done this correctly. So let's go ahead and try one more series circuit to see if we can apply these rules and kind of master all of this. So this is the circuit that we're given, and we have 3 resistors. Again, they're not all going to be equal ratings of how much resistance they have. So this one has 2 ohms, this one has 2 ohms, and this one has 1/2 of an ohm. The first step that you want to do in a chart like this where you have voltage, current, and resistance is just fill in what you already know. So we know the total voltage because that's what's labeled on the battery. So the total voltage that we're given here is going to be equal to 9 volts. All right, and we know the resistance of each individual component here. So we know the resistance of our resistor 1, that's going to be 2 ohms. For resistor 2, it's also going to equal 2 ohms. And then for resistor 3, it is equal to 0.5 ohms. Okay, and if we look at our rules for the series circuit, we know that the resistance, you can add them all up to get the total resistance for that entire circuit. So 2 plus 2 plus 0.5 gives us 4.5 ohms. So that's the total resistance if we were to add up all the resistors together. Okay, now we are missing the total current, but we can find that by doing Ohm's law. Remember, Ohm's law is equal to V equals I times R. So if we wanted to find the total current, we have to use the total voltage and the total resistance. So the total current, I total, is equal to the voltage total divided by the resistance total. So it's going to be 9 volts divided by 4.5 ohms. So in that case, we get the value of 2 amps. So what's really great about finding the total voltage and the total current is that no matter what kind of circuit you have, that one of these columns is going to be completely filled out for you, depending if it's series or parallel. Because in series, the current is going to be the same, but in parallel, the voltage is going to be the same. That being said, this is a series circuit, so we know that the current is going to be the same as expressed by this rule over here, right? So the current is going to be the same everywhere, so we know that we can put 2 amps all across this column. All right, and now it's just a matter of applying Ohm's law yet again. So here's Ohm's law. And we are going to apply it to every single one of these resistors to tell us what the voltage is at each location. 2 ohms times 2 amps gives us a voltage of 4 volts. 2 ohms times 2 amps again gives us 4 volts. And then 0.5 ohms times 2 amps gives us 1 volt. And once again, we want to double check our work with this equation. The voltage total is equal to voltage 1 plus voltage 2 plus voltage 3. So if we add all of these up, 4 plus 4 plus 1, that does indeed equal 9. So we know we did this correctly. All right, so we've taken a look at some series circuits, but what about some parallel? So take a look at this circuit right here, this schematic, and we can identify that it's a parallel by tracing the path from the battery and going back to the battery. So let's say we leave the battery this way and we're tracing the line. And right here, we see that the path diverges upwards and to the right. So we know that any single time the path is going to diverge like that, and you have 2 separate paths going back to the battery, you have a parallel. All right, so we have to recall now what the rules were for the parallel circuits because they are not the same as the rules for the series circuits. So the voltage in the series circuits, you had to add it all up. In this case, for the parallel circuits, the voltage is going to be the same. So whatever the battery is, that's what every single resistor is going to get. That's what every single component in a parallel circuit is going to get. They are all going to get the same voltage. So in our case here, we can fill out the total voltage being 9 volts. All right. Um, that also tells us, because of this rule that we just learned, that the voltage at resistor 1 is also going to be 9 volts, and the voltage at resistor 2 is also going to be 9 volts. So that makes it really easy. What about the other rules really quick? So taking a look at current, current is going to be the one that you have to add up. Similar to how we had to add up the voltage in a series circuit, we now have to add up the current in all of these parallel circuits. So the current does get split up between all the resistors, and we do have to add it up to find the total. The resistance rule is a little bit messy, and it involves finding the reciprocal of everything. All right, so it does get a little bit messy, but I will show you the way that we can kind of avoid this, and I'll show you a different way we can also calculate this using a different form of this equation. So the way we can find the total current is by first finding the resistance for everything individually. So let's go ahead and find the resistance for R1. R1 has a resistance of 2 ohms. R2 has a resistance of 2 ohms. So what we can do now is apply Ohm's law, which is V equals I times R. And we can find the current by dividing the voltage and by the resistance. So remember, current is equal to voltage divided by resistance if we just rearrange this equation. So in our case, we're doing 9 divided by 2 to find this current. 9 divided by 2 is going to be equal to 4.5, and that's going to be amps. And we have it again, 4.5 amps. So to find the current, by applying this rule right here, we can see that what we need to do is just add these two up. 4.5 plus 4.5 is simply 9 amps. All right, and to find the total resistance, all you have to do now, instead of using this really messy equation, I try to avoid this as much as possible, so we're going to use Ohm's law. To use Ohm's law to find resistance, just remember that it is indeed voltage divided by current. So 9 divided by 9 is 1 ohm. Notice that 2 plus 2 does not equal 1. So that trick that we had for series circuits does not work here. But if we wanted to apply it here, this is how you would do it. You would have to find the reciprocal of each one. So 1/2. I'm going to put this 2 because actually let me try to color code this really quick. So if we're going to make this resistor blue, so I'm going to put a box around this, and then this one orange. So the blue one, I'm going to put its value right here. And this is going to be 1/2 as well. Okay, so if we add this up, 1/2 plus 1/2, of course that is equal to 1. All right, but what you need to do after this is find the reciprocal of that because we have to carry this over. So it's just 1/1. 1/1, the reciprocal of that is just 1, so that's what we put here. Again, if you're not a math person, this can get definitely really messy, so I try to avoid it as much as possible. You can avoid it most of the time by finding the voltages for all the resistors, finding the individual resistances, finding the individual currents, and then adding up the current, and then finally getting the final resistance. All right, let's try one more parallel problem here. And this parallel problem, we have the same rules that we applied before. And we're going to first fill out what we know. So we know resistor 1 is 2 ohms. And we know that resistor 2 is 4 ohms. Right? Resistor 1 is 2, resistor 2 is 4. And we know the total voltage of the battery is going to be 9 volts. Okay, taking a look at our rules here for parallel circuits, we can also identify the voltage of everything else in the circuit because of this rule right here. This rule says that the voltage of the circuit is equal everywhere. So 9 volts total means that resistor 1 and 2 both get 9 volts. That being said, we know that the current can be calculated using Ohm's law, V equals I times R. Okay, so I is equal to V divided by R. So 9 divided by 2 in this case is going to equal 4.5 amps. And then we have 9 divided by 4. So if you did that in a calculator, you would get 2.25 amps. So now what we can do is use this rule. Okay, we know that the total current is going to be all of the components added together. Current 1, current 2, current 3, so on and so forth. So the current at resistor 1 is 4.5. The current at resistor 2 is 2.25. Add those two up, you get 6.75 amps. Okay? Now we can use Ohm's law again to find what the resistance is, because 9 is equal to 6.75 times some value. So that resistance is going to be 9 divided by 6.75. If I do that in a calculator, I get 1.33 repeating ohms. All right, so we completely avoided this equation, and that's a really good thing, because this is an equation that's kind of messy. But I am still going to show you how to do that in case you do want to know. So 1 over R1. R1 is going to be this value right here. So I'm going to put a blue box again around 2, just a color coordinate. And then 4 ohms around this one right here. So what we can do is just start filling in values for this. So let me just go ahead and copy down this equation. And instead of R1 here, I'm going to put the actual value. So R1 was 2. And R2 was 4. Okay, so what we're actually going to do first here is figure out what 1 over 2 plus 1 over 4 is. And of course, we know that to be 3/4. Okay, so it's basically 1 over 3/4. Okay, and so whenever you have a reciprocal like this, where it's 1 over like this, all you have to do is flip the denominator and the numerator. And so you get 4 over 3. And 4 over 3, if you did that mathematically in a calculator, you would get a decimal of 1.33. In case you're curious of how to type this into a calculator, instead of doing like 1 divided by 3 divided by 4 and having to put in all those parentheses, another way you can do it is if you did 3 divided by 4 and did the entire thing to the -1 power. Doing it this way will also give you the same answer, whether it will give you the fraction 4/3 or it'll give you the decimal 1.33. All right, because these parallel circuits are a little bit complicated, we will try to do one more, and we're adding another resistor to this. So we're going to complicate it even a little bit more. The first tip that I like to tell people is to go ahead and just fill out what you know. So we know the total voltage of the battery, that's going to equal 9 volts. And we know the resistances of each individual resistor. We know that resistor 1 is going to be 1 ohm. We know that resistor 2 is going to equal 2 ohms. And we know resistor 3 is also going to equal 2 ohms. The next thing that we can figure out with a parallel circuit is taking a look at this rule that the total voltage is going to be the same everywhere. We can fill out this entire column. We know that the voltage is going to be the same. Next, we can apply Ohm's law, where V equals I times R, to figure out what the current is, because if we rearrange this, it tells us I is equal to V divided by R. So 9 divided by 1 in this case is going to give us 9 amps. 9 divided by 2 in this case gives us 4.5 amps. And once again, 9 divided by 2 gives us 4.5 amps. Now the total current can be calculated from all of this, because the total current is added. So 9 plus 4.5 plus 4.5 again gives us 18 amps. And then, of course, finally, the resistance. We could just apply Ohm's law. The resistance, to calculate that, it's going to be the voltage divided by the current. So resistance is going to be 9 divided by 18. So the resistance for this entire circuit is 0.5 ohms. Okay, and to do that mathematically, again, I'm just going to show you how to use this equation. We filled out this entire chart without having to use that equation, but again, I'm going to show you how to do that. Resistor 1, I'm going to put blue. It's going to be 1 ohm. Resistor 2 will be orange, and then resistor 3 will be green. Right, so mathematically, the way you would do that is 1 over plus 1 over plus 1 over. And then I'm just going to fill in this value. So 1 over 1 plus 1 over 2 plus 1 over 2 again. Okay, 1 over 1 is just 1, and then 1 half plus 1 half is also 1. So to simplify this entire thing, we have 1 over 2. So that actually turned out that we have a really nice fraction for this. We don't have to do any reciprocals or anything. 1 half, we can easily turn that into a decimal. So the entire resistance of the circuit is 1 half ohms. 1 half as a decimal is 0.5, and that's where we have, and that's what we have in our resistance total. Okay, so now that we have a good understanding of both series and parallel circuits, we want to ask ourselves the question, what if you combine the two together? What if you have a series parallel circuit? What do you do then? Which rules do you follow? So we're going to actually take a look at an example, and I'll show you how to dissect this problem so that we can actually identify what do you do within a series parallel circuit, such as this one that we have here. I went ahead and copied down the rules for both series and parallel. Series is going to be in red. Let me go ahead and just jot down series right here. And then parallel is going to be in blue. So I'm going to put parallel so that we know the rules for both of these. So what you want to do first with a circuit like this is actually you want to split it up first by condensing it together so that you can find the total equivalent resistance and the total equivalent voltage, and then hopefully you can find the current from there. The only thing that we can fill out right now is that resistor 1 is at 2 ohms, resistor 2 is at 2 ohms, resistor 3 is at 2 ohms, and the total voltage, which is 9 volts. We cannot find out what the total voltage is based off of the parallel or series rule, nor can we do the current rule either. So we are pretty much out of luck on those things. But this is how you go ahead and find those values. What you have to do is condense the entire thing together, and this is how you do it. You go ahead and take this circuit and find the areas where you can condense it. And basically what you want to do is find something that has in common. So this is the only one that's in series. So this is resistor 1, and it's in series. But these two are in parallel with each other. So these two right here, they can be condensed to have one what's called an equivalent resistance. So what I'm actually going to do is I'm going to sketch out this circuit, kind of do like a rough sketch here. So we have our 9-volt battery. We still have resistor 1, okay? And then in red, I'm going to sketch the equivalent of these two. So I'm just going to do a resistor here, just like that. Resistor 1 will be the same. So resistor 1 is going to stay here, and it's still 2 ohms. We're going to call this resistor 2, 3. Okay, so this is going to be a fake resistor. It's basically the equivalent of these two. This is not a real thing, but it's the equivalent resistance if we were to combine resistor 2 and resistor 3 together. Okay, and the way we do that is by taking a look at the rules for the resistors for this. Now these are in parallel with each other, so we have to use the parallel rules. So here are the parallel rules, right? And we're trying to find the equivalent resistance of those two. So the equivalent resistance of those two resistors can be calculated by doing the reciprocal rule that we have here. So resistance of that particular part of the circuit is equal to 1 over 1 plus R1 plus 1 over R2. And we only have those two, so that's all we have to worry about. So let's go ahead and do that really quick. If I have 1 over the 1 over 1 half, so it's going to be like that because it's 1 over 2, and I have the 2 here, plus 1 over 2 again. Okay, and if I simplify this, 1 half plus 1 half is just equal to 1. So this is just 1 over 1, which is simply 1. Okay, so the equivalent resistance that we have here is 1 ohm. Now keep in mind, this is not a real resistor. This is just if I were to make these two circuits and I needed a 1 ohm resistor, I could do like a 1 ohm resistor here, or I could put 2 ohm resistors in parallel with each other. So these two equivalent circuits they're running basically the same way. So what I'm actually going to do now is for this chart, I'm going to put those resistances here. So I have R1 here, then I have R2, 3 over here. And I'm going to put those resistances here. So R1 was 2 ohms, and the equivalent resistance for R23 we determined to be 1 ohm. So in this case, we found the total resistance, okay? How do I know we found the total resistance? Because we've limited this entire thing, so we've condensed this until we only had a series. You can identify that this is a series by following the path from the battery. I can make my way all the way around, and this is only one path. Okay, so I've condensed this as much as I could, and what I'm going to do is now combine these two resistors using another rule. So I'm going to go back to this page to see what that rule is. Since we're dealing with a series, that resistance now is going to be R1 plus R2. Okay, so R1 plus R2, in this case our R2 is this combination. We can see that the total now is going to be 3 ohms. Okay, so that's the total resistance. And we can actually go back to this page and fill that out. So now we have an equivalent total resistance of 3 ohms. Using Ohm's law, we could do 9 volts is equal to some current times 3 ohms. That current is going to be 3 amps. All right, we don't know exactly what the current is because, again, in this diagram, this is a series parallel. We can't necessarily follow any set of these rules, but we can if we condensed it. So this was a series, so we're going to use a series rule for current, and current is going to be the same. Okay, so we found the voltage was 9 volts, and the current was going to be the same, and the total current was 3 amps. So current is the same everywhere. Okay, and now we just use Ohm's law to find the voltages for this particular circuit. 2 times 3 gives us 6 volts, and then 1 times 3 gave us 3 volts. Okay, we're going to hold off on this one resistor for now, this combination that we did, but we do know the information for R1. Okay, so now R1 is all filled out. It's 6, 3, and 2. So we can actually go back to R1 here and fill out this voltage is 6 volts, and the current was 3 amps. Okay, and again, what I did here was I just took R1, and the values that we found for it, we found by doing this table right here. All right. The final thing that we're going to do is take R2 and 3, which is this, and split it back up so that we can keep them as individual resistors, so R2 and R3. Now recall that R2 and R3, they are in parallel with each other, as you can see here. So in parallel, we need to identify what's going to be the same in parallel. Is it voltage that's the same, or is it current that's the same? And by looking at the rules here, we can see that voltage is indeed the same. So even though these things are together, the total voltage for these two are together is going to be 3 volts. They individually also get 3 volts because they are in parallel with each other. So R2 gets 3 volts and R3 gets 3 volts. So now what we can do is just do Ohm's law and figure out what the current is. So in this case, I is equal to V divided by R. So 3 divided by 2 gives us 1.5 amps, and 3 divided by 2 again gives us 1.5 amps. So this was kind of like a really tricky problem. I'm not expecting any of you to understand how to do one of these problems fully, like a really complex one. I also don't expect you to do this on a test or anything like that. This is just showing you how the rules for series and parallel can be combined together, and you can get all sorts of different voltages and currents depending what your circuit looks like. What I'm going to do now is offer an extra credit opportunity for everyone here. So you can take a look at this, and I'll leave it here for a little bit. And what I would like for you to do is copy down this circuit and fill out this entire VIR table. So this is a series parallel. And using the technique I just showed you, what I would like for you to do is fill this out. And again, this is an extra credit opportunity. You do not have to do this. I don't expect anyone to really understand how to do this, but I'd like for some of you to at least try, give it a shot. If you get all of the values here for the VIR table, then you will get the extra credit. So it is an all or nothing thing. You have to get all of it correct in order to get the extra credit, and I'll award points to whoever can get that.